today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Theshani give us a talk on multivariate fidelities. So Theshani is a fourth-year PhD candidate at Cornell University. So she's advised by Mark Wilde and Ziv Goldfeld. Her research is on the interconnection of like classical and quantum information theory, privacy and statistical learning. So she received her bachelor's from University of Moratuwa in Sri Lanka, master's degree in Cornell University. Before joining Cornell in 2021, she was a lecturer at University of Moratuwa and also a research intern at the Singapore University of Technology and Design in 2017. And from May 2024, she has been this graduate TA development consultant in the College of Engineering in Cornell. So Theshani, the floor is yours.
Yeah, thank you for the kind introduction and also thank you for the invitation and thank you for everyone who is here for my talk. So today what I will be talking about is one of our recent work on multivariate fidelities. This is a joint work with Hemant, Felix and Mark. So to give a sense of where we are heading to, I'll talk about some backgrounds related to this. So as we all know, distinguishability and similarity are essential concepts in most of the scientific disciplines. In quantum information theory or like classical information theory, distinguishability measures like quantum relative entropy, Kullback-Leibler divergence in classical information theory, those are distinguishability measures that we use a lot. And what we are going to talk in this talk, what we are going to look at in this talk would be similarity measures. So in when we think about similarity measures between probability distributions, there's a quantity called Bhattacharya overlap. I will give formal definitions of these later, but for now let's talk about what's existing and what we are heading towards. So between quantum states, we have fidelities which quantify the similarity. Uhlmann fidelity, Holevo fidelity are some of them. And then let's say if we want to characterize the similarity between a collection of probability distributions, more than two probability distributions, there are some quantities like Matusita affinity, which is also known as R-through fidelity, and also average pairwise classical fidelity. Those are some extensions that one could have for the to extending the similarity between probability distributions to more than two. What we are targeting in this talk is, let's say we have a collection of quantum states and we are going to find out the similarity between those, what is the similarity of that collection. In that, uh, the quantum generalizations of these multivariate classical fidelities has not been systematically explored. That's what we are targeting at through this work. And we are finding quantum generalizations of the classical multivariate fidelities. And also we show that they satisfy desirable properties, and also they are natural generalizations of the bivariate fidelities that we know. So that's the main thing that I'm going to head into it. And as I promised, I will go through some of the mathematical preliminaries that we will need for the talk. First, let's consider that we have two probability distributions, P and Q, and then we want to find out the similarity between these two probability distributions. That's to quantify that, the Bhattacharya overlap, which is also we can call as bivariate classical fidelity, can be quantified as this overlap between the probability distributions P and Q, and it would be quantified as follows. And then there are infinite number of similarity measures that generalize this Bhattacharya overlap to quantum states. For that, let me introduce a quantity called z-fidelities. C, when C is greater than half, that's exactly equal to this. And how this quantity was originated, it was from alpha C Renyi relative entropies, which were introduced by Ordonat and Nilanjana in their work. And what we can do here is, if we fix alpha to be half and look at the trace functional in this d alpha c, what we would get is c fidelity, as we called as c fidelity. And what is nice about these quantities is that for z greater than half, these obey data processing. So they are quite nice quantities in terms of quantum information, as data processing is one of the main properties that we are looking for in a quantity when analyzing this, both the distinguishability and similarity measures. So if we look at C fidelities, this actually generalizes the things that we already know, the fidelities that we already know. One of them is Uhlmann fidelity. If we fix C to be half, then it is nothing but Uhlmann fidelity as quantified, and as can also be written as follows using the trace norm of square root of rho and sigma. And note that we are not taking squared here, like if you might have seen fidelity with squared, but in this talk we will, when we say Ullmann fidelity, what we are looking at is the following one. And then if we fix C to be 1 in the following quantity, what we will get is Holevo fidelity. You can exactly see it from the expression by fixing C to be 1 and then using the cyclicity of trace. And another quantity that arises from this framework is, if we choose Z to be, if we think of the limit C goes to infinity, this gives a fidelity which is also seen as log-Euclidean fidelity. So how this comes, the last equality comes through by applying a Lee-Tolte kind of product formula. We can arrive at the following expression. Why I'm presenting all these things is that I will look at the quantum generalizations of these to multiple states in this talk. And if you have any questions, you can ask in the middle of the talk. I might not see the screen, so it would be better if you can ask the question verbally, and so these are the preliminaries related to the bivariate fidelities that we know. And one of the common and the mostly used fidelity is Ullmann fidelity. And Ullmann fidelity can be written in different forms. As I introduced initially, we can write it as the trace norm kind of expression. And also the second one comes from Ullmann's theorem, where we look at the purifications of the state rho and sigma, and then consider the following overlap with U being unitaries. And then the third one is also important because it shows that fidelity can be achieved by a measurement, which is a nice property and then can be utilized in different forms. And the last two are semi-definite programs for Ullmann fidelity, which was due to the work of Walters. And then this shows that those can be computed using semi-definite program solvers. So I'm presenting this because I will use the different forms of Ullmann fidelity to get inspired to propose several multivariate versions of this. So the main goal, as I stated before, is to identify the measures for quantifying the similarity of a given tuple of states. If you are given a tuple of states and we are looking at how similar they are. And the main approaches that we are going to take to arrive at these, the box with multivariate quantum fidelities, one way is that we will look at the multivariate classical fidelities, and then we will try to generalize them to the quantum setting. So this is one approach. And another approach would be, we look at the bivariate quantum fidelities and then try to generalize them to multivariate quantum fidelities. So these are the main two approaches that we are taking. But sometimes when we propose one quantity, that quantity can be arrived from both the ways. So those kinds of things will come across as well. But these are the main intuitions that we used when proposing these quantities. And there are a bunch of them, but I will talk about some of the important ones out of these during my talk. Are there any questions? Okay.
I just wanted to clarify something.
Sure.
I mean, so when you limit the z-fidelities to
Uh-huh.
1/2, to bigger than 1/2, this is only because of the data processing
Yeah.
inequality.
Yeah.
Because if you take lower than 1/2,
Yeah.
it doesn't have this property.
Yeah, it doesn't have. That's
Okay.
one of the
But
reasons that.
mathematically, I mean, of course, you could still define it, I suppose.
Yeah, yeah. I will in like the main motivation here is we are trying to look at a certain kinds of properties that a fidelity should satisfy, and we demand data processing to be one of them. So that's one of the reasons that we care on the regime that data processing holds.
Okay. But it doesn't mean that, okay, so if it holds for that regime for bivariate, it doesn't necessarily mean it will still hold for a multivariate extension of it, right?
Yeah,
But
that's not clear, but for the generalizations that we define, we proved that it satisfied data processing. So I will go over, when I'm going over the our generalizations, I will discuss more on that.
okay,
Maybe,
sure. Yeah,
yeah,
okay.
yeah. Thank
Okay,
you for
thank
the
you.
question. Yeah. So now we have looked at the bivariate setting, and now let's move on to the classical multivariate fidelities. So if we are given a collection of probability distributions P1 to PR, uh, the classical multivariate, one of the classical multivariate fidelities is average pairwise fidelity. So this is, we care about the fidelity between each pair, and then we take the average. And note that fidelity satisfies symmetry. So fidelity of pi pj is also equal to fidelity of pj pi, which is an essential thing for a similarity metric measure. So that's why we have this 2 times r over r minus 1 as the normalization factor. So these are for the probability distributions on a finite set. And for commuting states, uh, also now because commuting states can also be observed as probability distributions if we look at the spectrum of the states in the common eigenbasis that they are commuting, and then we can define uh, the average pairwise fidelity for commuting states as well. And another known multivariate classical quantity is Matusita multivariate fidelity, which is also known, which was introduced by Matusita, and then it is related to this R-root fidelity. Here, the generalization is like earlier when R was 2, we were looking at the square root. But now what if we consider the R-root of the probability distributions? So it's the quantity of interest there. And then for commuting states, as previously, we can look at the spectrum of the states and then define the following. And one of the important inequalities between these multivariate classical fidelities, the two things that I defined are the following. That average pairwise fidelity is always larger or equal to R-root fidelity, and why and then this holds by simply using arithmetic mean, geometric mean inequalities to this setup. And in our work, we looked at another variant that can be a multivariate classical fidelity, which is average k-wise fidelity. So this is something which is interpolating between the average pairwise classical fidelity and Matusita multivariate fidelity. So this would say that we choose k from our states, we choose k of them, and then we evaluate the kth root fidelity. That means kth root Matusita fidelity of order k, and then we average over such k subsets that you can obtain, which is the normalization factor is given by this R choose k inverse. And what we can show is that the interpolation, where the smallest is the Matusita multivariate fidelity when we choose k to be R, and average pairwise classical fidelity comes when we choose k to be 2, and then this nice interpolation happens with this. So these are kind of multivariate classical fidelities that we looked at in our work and from the existing works, and some generalizations like average k-wise fidelity. So these are the classical, multivariate classical fidelities. Now what we are looking at is, can we generalize these multivariate classical fidelities to the quantum setting? So we are using the first approach and looking at what kind of quantities that we can arrive at. Before that, we will look at like there can be different generalizations that one could look for, but we would we would expect some of the properties from multivariate fidelities as follows. So this, if our quantity that we define satisfy these properties, then it's really good. So that's what we are aiming at from this set of properties. So the first, we demand that any multivariate fidelity that we define should reduce to multivariate classical fidelities. So this is one of the important things that we like to look at, because apparently at the end of the day that it should be a classical thing would be a special case of the quantum one. So we need the reduction to the multivariate classical fidelities. So we talked about three quantities. First, it could be equal to the average pairwise quantity, or the Matusita multivariate fidelity, the rth root 1, or the average k-wise fidelities, which is a interpolation between these two. So that's one of the properties that we are demanding to have. The next would be data processing. As if I refer to the question earlier, we were also we would like to have data processing in a quantity if we define multivariate generalization. So what data processing does is, if we have a set of states rho 1 to rho r, and if we process them through a common channel, then we want this fidelity to be larger, because when we process through that tunnel, we expect them to look more alike or like more similar because of that evolution. So this is one of the properties that we look for. And also symmetry, that is also important for a similarity measure, that if we are given rho 1 to rho r, and if we, for any of the permutations of these states, still the fidelity should be the same. And one other thing is faithfulness. If fidelity of a set of states is equal to 1, we want that to happen if and only if all the states are the same. So this is one of a nice property for the for a similarity measure as well, because if they are equal, then they are similar. So it should take the maximum value that one can take in this case. And this property I would talk about more in when we are talking about generalizations, because some of the generalizations might not satisfy this completely, because so one thing is, we want if the fidelity is equal to 0, if and only if the states are orthogonal to each other. If we look at the classical variants, average pairwise fidelities satisfy this, but the r-truth fidelity in for even for the classical state probability distributions, it will satisfy the fact that if the states are orthogonal, it would be 0, but it might not satisfy the fact that if we have the fidelity to be equal to 0, it doesn't mean the states are orthogonal. So any generalization of the Matusita multivariate fidelity will disobey one side of this orthogonality, and I will show one of them when I discuss them. And another property that we would be interested to have is direct sum property. This is if we consider a collection of CQ states with the same probabilities or probability distribution in the ensemble, we would expect the following to hold. So these are some properties that we would like to see in a multivariate generalization that I will introduce. So let's look at one of the easiest or the closest generalization that one could do. So we have average pairwise fidelities. Now we can do the same for average of the bivariate fidelities that we know. So for z greater than half, we define the average pairwise z fidelity as follows. And then for c equal to 1, then we saw that c fidelity reduces to Holevo fidelity. So where in this quantity also we will get average pairwise Holevo fidelity, and then for z equal to half we will get average pairwise Uhlmann fidelity. And then this we showed in our work that this quantity satisfies all the desired properties that I mentioned previously, and most of the proofs use the fact that C fidelity satisfies these properties, and then it follows from there. And I will show, and after showing some of the generalizations, I will show some inequalities which help us to prove things immediately for a certain class of generalizations. So this is the easiest generalization that one could look for. And now I will define something different from that generalization. Earlier, we are looking at the average multivariate classical fidelities and trying to look at the generalizations from there. Now, for this one, we basically consider the second approach. We looked at the SDP for the bivariate Uhlmann fidelity. So if you look at this, the constraint over here, it can equivalently be written as follows. Between y1 and y2, and then in the off diagonals, we will have identity. And now what I'm trying to do is we look at this SDP and we are looking at what kind of generalizations that one could look for in this for multivariate setting. So we propose the following. The main one thing that one could look at is if you look at the constraint, I generalized it for the quantum set for the multivariate case by pushing all the yi's on the diagonal and demanding the other matrix over there to be identities except for the diagonal one. And then if we look at the constraint objective function, it was a summation over all the trace of yi rows. So I could look at this as a summation of the overlaps between yi's and row i's, and then sum over that. So if we substitute r equals 2 here, and it will generalize, it will be the SDP of the bivariate Uhlmann fidelity is a special case of it. So that's one way we are looking at, and one could also look at this objective function over here and consider some geometric connections or anything of that kind. But what we look in this quantity, what we wanted to have is an SDP computable multivariate fidelity. So in this, so we tried to make sure the one that we are getting is also SDP or is also an SDP. And then we showed that this quantity also satisfies all the desired properties that we demanded initially. So it's nice. And now this is an SDP. So it should have a dual. So we could show that the following duality holds. And then here, if we look at the what was other SDP, it's actually a generalization of that to R greater than 2. And then this normalization also works right with that. Next, the equivalent formulation that I present here, it's not obvious. It it's it was obtained with several uh, connections to other equivalent representations that one could look for the SDP fidelity. But I would give a hint of how we obtained this. Initially, what we were interested is about this, why we were interested in something like this is basically we wanted to have a formula that looks like Uhlmann's theorem for a bivariate case, but what we obtained was not essentially like that, but something looks like that. So as here, this psi is something which is related to the purifications of the states rho I, and then we look at this overlap with the k tensor ID with this large state. And when we obtain this equivalence, initially we showed it for the case where the states are positive definite states, and then we proved that this specific quantity over here satisfies a certain uniform continuity, and then that uniform continuity helps us to uh, take our result from positive definite states to the case of all general states. So to show something with those uniform continuity, this is the kind of uniform continuity that we proved is if we have a collection of uh, rho i's and sigma i's, and then we want to see how close the SDP fidelities are. If we have a certain condition on the state's fidelities, like average fidelities of the rho i's and sigma i's, we would get the following. So if we have the following condition, we would have a uniform continuity in as follows, where when epsilon goes to 0, we would have these quantities to be equal. So this is one of the ways that we used to prove this equivalent representation that I showed previously. So that equivalent formulation was helpful in proving certain properties and also some connections to other quantities of interest. So there's another equivalent representation of the above quantity that I would like to pinpoint is that, like, if you look at the previous definitions, it's not that clear that SDP fidelity is an average pairwise quantity, because even though it's a summation and average, but it was not clear whether it's an average pairwise quantity. But the following equivalent representation, which we derived in the middle of deriving the other quantity that I showed previously, it shows that it's indeed an average pairwise quantity, because if you look at the objective function over there, it's with the purifications of the state rho I and rho j, and then we look at the overlap. So this shows that the multivariate SDP fidelity is itself is an average pairwise quantity. So this is this quantity was mostly inspired by the SDP of the bivariate setting. And now we have talked about two different generalizations. I will look at another generalization to the multivariate case, which we call as secrecy based multivariate fidelity. Why we named it as that would be clear by the fact that we have the following secrecy measure from Robert Renato and Christian's work on operational interpretation, meanings of min and max entropies. The following secrecy measure has come up. So what we do is we fix a state sigma and then find out the average fidelity with respect to each row wise and supremize over all sigmas that can in the sigmas of the same dimension. And this can equivalently be written using the fidelity between a CQ state, rho xa and rho x and sigma, where the following are equivalent. So what we do here is we define the secrecy-based multivariate fidelity as follows. We look at this S, which is the secrecy measure, and we squared it and then multiplied it by R and divide and minus 1 and then normalized by R minus 1. And this normalization is essential because of the fact where S lies. In fidelities, we were also looking at the fidelity between quantum states to be between 0 and 1. So this normalization is essential over there. And then this quantity also satisfies all desired properties that I stated before. So to prove these properties and also to find connections, we derived an equivalent representation to that quantity. So the equivalent representation goes as follows. We have purifications of the states rho I as phi rho j and phi rho I, and then we have these unitaries vj's, vi's, and then we look at its vj dagger vi's, and then look at the real part of it. So this quantity is essentially looked at, like a similar format has been looked at in the following work of estimating distinguishability measures on quantum computers. In that work, there is one connection to a quantum interactive proof, and then this quantity appears as the maximum success probability. So I will not talk about like what exact quantum interactive proof that it would take, it would evaluate to, but if you are interested, you could look at this paper to have an idea about what what kind of interactive proof that gives uh, the following quantity as the success probability. And then that itself says that this quantity has an operational meaning in terms of secrecy, because it was based on a secrecy measure. Yes, then we have a operational interpretation through that, and also through an quantum interactive proof is maximum probability of accepting it. Now let's do some simplifications to this. So we have unitaries over here, vj's. If we fix vi's over here to be identity and purifications to be a canonical purifications, uh, then we can show that this expression evaluates to be the following. And then if we look at that, it would be a specific choice. So that choice will be always upper bounded by fs, which is the supremum over it. So the quantity over here is nothing but the whole average pairwise Holevo fidelity. So what we showed here is average pairwise Holevo fidelity, which is when z equals to 1 in the average pairwise C fidelities, is always lower bounded, or always a lower bound to Fs, which is secrecy based fidelity. So why I'm going through this is I'm trying to build up the connections between the quantities that I defined previously. Now, uh, let me recall the SDP, the equivalent representation that I showed for FSDP. And then the second expression is nothing but the one that I showed for the secrecy-based fidelity. And if we choose these Kij's in the first SDP to be the unitaries like Vi dagger Vj for all Ij, then we can show that this is a possible candidate for the optimization of the FSDP. And then that essentially shows that if I plug that value into this into the first SDP, it would be a lower bound to the FSDP because it's just a choice and we are supremizing over all Ks. And then if I supremize over all VIs, the quantity over here is evaluating to Fs, and hence we have that Fs is in between is larger than FSDP. So now we establish two inequalities. Holevo fidelity, average pairwise Holevo fidelity is upper bounded by Fs and Fs is upper bounded by FSDP. Let me say the first two inequalities is something that you have seen with the different expressions that we obtain for each one of them. And the next one between SDP and average pairwise Uhlmann fidelity, that also comes through using the SDPs and finding right choices. And this last inequality holds from the fact that we have the relation that Uhlmann fidelity is always upper bounded by square root of Holevo fidelity. So using that fact, we can show the the last inequality. What is nice about this is if we look at the FH, which is Holevo fidelity, average pairwise Holevo fidelity, and average pairwise Uhlmann fidelity, both of these are z-fidelities and also they reduce to average pairwise classical fidelity for commuting states. So that says that uh, everything in between them also reduces to average pairwise classical fidelity for commuting states. So it's nice. And also the following says that all of them satisfy faithfulness and orthogonality because we have fh and then also we have the square root of fh on the other side. So these two implications and the things can be proved easily from the inequality that we proved here, and the technical arguments related to these comes when establishing these inequalities, finding the equivalent representations, and then combining them. So before moving to the next one, are there any questions? Okay, if there are no questions, let's move on to the next one. So far, what we looked at are generalized. If you see them here, we could show that all of these generalizations reduce to average pairwise classical fidelity. But we talked about another classical variant, which is average pairwise, which is related to Matusita multivariate fidelity. So now let's look at a generalization of that, which we call as multivariate log-Euclidean fidelity. So it's inspired from the following quantity, which is the multivariate log-Euclidean divergence. Let's define it for positive definite states first. So if we have a set of positive definite states and a probability distributions S1 to SR are the probability mass atoms, and then we can define the multivariate log-Euclidean divergence as follows. And then what we will be doing is that For commuting states, we can show that Hs is equal to the following. And if we look at the trace part, if we forget about the minus log and the trace part, this essentially gives us a hint that if I fix Si's to be 1 over the uniform prior on it, then it is essentially the Matusita multivariate fidelity that we looked at for commuting states. So in the setting when we talked about the classical variant. So this is what we are aiming at. We are going to fix these SIs to be uniform prior 1 over R and then define a log Euclidean fidelity. And for general states, also this divergence can be defined by considering rho i's to be rho plus epsilon I, and then take the limit using infinite. And to be clear, then we defined the multivariate log-Euclidean fidelity. So what we did here is we looked at the trace functional over which was appearing in the multivariate log-Euclidean divergence. And now we look at the following with the uniform prior 1 over R. And for the general case, as previously, we can define rho i's if rho I plus rho I epsilon is defined as rho I plus epsilon identity. So now these are positive definite states, and then we can use the first definition and then take the limit. And what's nice about the multivariate log-Euclidean divergence or log-Euclidean fidelity is that it also satisfies all properties of a desired multivariate fidelity except for the complete orthogonality. So for an orthogonal collection of states, we have the fidelity to be equal to 0, but if the fidelity is equal to 0, it doesn't imply the states are orthogonal. So for that, you can basically look at this count example using probability distributions, which is essentially one case where if I have zeros on 3 different places, and when we take the overlap, each term evaluates to 0, but all these states are not orthogonal. So this is one count example towards that. And so far, we now have different quantities with pairwise fidelities and this multivariate log-Euclidean fidelity. One could show the following, that this multivariate log-Euclidean fidelity is always upper bounded by pairwise z-fidelities when c goes to infinity, which I introduced as log-Euclidean fidelities. And this also now we can put where the multivariate log-Euclidean fidelity comes in the chain of the inequalities that I showed. So because of the fact that C fidelity has a certain kind of monotonicity, so this quantity average pairwise C fidelity for Z going to infinity will be always upper bounded by a C which is less than when for the C, if we choose C to be 1, then we have Holevo fidelity, and then we have the following chain, and we complete where this multivariate log-Euclidean fidelity lies on there. And one thing nice about this is that multivariate log-Euclidean fidelity can be equivalently written as follows. This is nice because this helps us to prove some nice properties for this quantity using the following expression. And if we look closely on this, the thing which is inside the exponent without the minus, it's the relative entropy. I forgot to mention that D refers to quantum relative entropy. And if we look at quantum relative entropy between rho x tensor sigma and rho xa, this quantity looks like a quantity that we all know, which is Holevo information. Holevo information is nothing but the quantum relative entropy between rho xa and rho x tensor sigma, and then we infimize over sigma. So we define this quantity to be Holevo information, which is the reverse of Holevo information. So this is inspired from the fact that mutual information and low term information is there in so low term is the reverse of mutual, and it's nothing but the exchange of the symbols from right to left over the here the word. So this is Ovelo information as we define, and then we can find an equivalent representation to uh, the multivariate log-Euclidean fidelity using this Ovelo information. And why I'm showing this formalism is that we could use this nice characterization to prove some properties when we were proving whether this quantity satisfies the desired properties of the quantity. So uh, so why I'm talking about these quantities, and then like we looked at the secrecy based one, we could find an operational interpretation through secrecy and application, and also through a quantum interactive proof. Now we can also show that this multivariate log Euclidean fidelity has an operational interpretation in terms of hypothesis testing task that I will introduce. So to show that, I will show that this operational interpretation holds more generally to multivariate log Euclidean divergences, which we obtain these multivariate log Euclidean fidelities. So let's consider the following setting. So then if we choose the null hypothesis to be following, which is an arbitrarily varying null hypothesis. So this is basically like we don't know the exact state that can come up in each mode, and then the collection of the pi set is a collection of all the states that can be obtained as follows. And then the second set is the simple alternative hypothesis, which is nothing but we have this CQ state, and then we take tensor product of those end states. So the hypothesis test is to determine whether this n mode state lies on this arbitrarily varying set, or the set that we looked at, or in the collection of the row S tensor n. So this is the task that we are at hand. So we can define the type 1 and type 2 error probabilities as follows. So for the type 1 now error, we have an arbitrarily varying null hypothesis. So we have to supremize it over all possible states that can come on there, so that we can evaluate the type 1 error. And for the type 2 error, we can find out we can define it as beta. And then we can define the optimal non-asymptotic type 2 error exponent. So in that case, what we do is nothing but we fix the type 1 error to be less than epsilon and infimize the type 2 error. So that's the error probability. And then as we define the error exponents, we will have minus log probability of error divided by n. And here we will infimize over all possible measurement operators. And we can show that if we take the limit n goes to infinity, this reduces to the following, where we provide an operational interpretation to the log-Euclidean multivariate log-Euclidean divergence. And this is due to in this proof we use the theorem 1 of Janis' work on hypothesis testing on on invariant subspaces of symmetric, uh, and then also it talks about arbitrarily varying sources. And from that work, we can arrive at the following expression. And now what we have is the fact that if we fix the probability size to be 1 over r, then the minus log fidelity, minus log Euclidean fidelity will have an operational interpretation from the same setting by fixing 1 over r and then minus log fidelity will have the operational interpretation. So that's one of the interesting things that we came across through our work. So I will also say some of the multivariate variants that we looked at, some other ones. So one thing is average k-wise log-Euclidean fidelities. So this is something similar to average k-wise fidelities that we define for the classical fidelities. And this will be a interpolation between average pairwise fidelities and log-Euclidean fidelities. And also we define as the which is natural that we looked at the minimal extensions of multivariate fidelities and maximal extensions of multivariate fidelities. And also we looked at multivariate geometric fidelities with the similar techniques that I showed previously, but I will not go more over that. But if you have any questions, I would be happy to answer on them. I think I will conclude what we have learned so far. So, what the main motivation behind this work is, we have similarity measures to find out the similarity between two states bivariate setting, and now we want to characterize the similarity between multiple quantum states. So this is what we did in our work, and we proposed several variants of the for the quantum case that reduce to average pairwise fidelity, which are average pairwise z-fidelities, multivariate SDP fidelity, and also secrecy based multivariate fidelity, inspired by first from the SDP of the Uhlmann fidelity and the other one from the existing secrecy measure. And we also analyzed their mathematical properties, data processing, faithfulness, and uniform continuity bounds. One thing that I didn't talk much about is that most of these quantities have these uniform continuity bounds that I didn't talk for each one, but you're welcome to look at our paper if you're interested. And then we proved that multivariate SDP fidelity and secrecy-based multivariate fidelity are actually sandwiched between the average pairwise C fidelities with C equal to half and C equal to 1. That's one of the inequalities that we derived in our work. And also we defined this quantum extension of the Matusita multivariate fidelity, which we called as multivariate log-Euclidean fidelity, and we analyzed its properties and also provided an operational interpretation in terms of quantum hypothesis testing with an arbitrary variant null hypothesis. So, like previously, what we were talking about is about what we have done in this work, and we are looking forward to the following. First is that, are there any information theoretic tasks that provide operational interpretations to these quantum generalizations, including the average pairwise C fidelity and multivariate SDP fidelity? So through our work, we provided operational interpretations to this secrecy-based multivariate fidelity and also uh, the multivariate log-Euclidean fidelity. But we are excited if if we could find out the information theoretic tasks that give operational interpretations to other quantities, and also we would like to call some other multivariate generalizations that would have operational interpretations as well. And one natural question is like, if we want to find out the similarity measures of a tuple of channels, so how can we do it? And that's also one natural question that one can look at. One option towards that is by extending the SDP of the fidelity of two channels to the multivariate case, and then look from there. So we would be excited to know what other avenues one could do. So we all ways the main thing, or the main way we tackle these things is like, we looked at what is existing in the class for the classical setting and also the bivariate setting, and look for the generalizations. So this question is basically from the second approach, because we know that Holevo fidelity has the following SDP, and can we extend these to the general multivariate case, it was not clear to us that it provides we could not get anything of uh, multivariate generalization of that, but it would be exciting to figure out if there are any multivariate generalizations using these kinds of representations to Holevo fidelity. So with that, I'll conclude my talk and thank you for listening, and I'm happy to take any questions if you have. Thank you.
All right. Thank you very much for very nice and informative talk. So yeah, so we have time for a few questions. So if you have a question, you can just unmute yourself and ask them now. Okay.
Yes. Yeah. So thank you for the nice talk. So I want to ask more general question. So
Sure.
in your first part, you propose several fidelity, which can be sandwiched between each other, and later part you propose the log-Euclidean fidelity.
Yeah.
So can you compare the two classes of fidelity? What's the difference between them? Usually, what's the purpose of the two classes?
So the one class is a generalization of average pairwise fidelities. The other class is a generalization of Matusita multivariate fidelity, which is like the Rth root fidelity. So those are two different classes. And this actually recently in one of the works, it has been shown that this multivariate log-Euclidean fidelities, multivariate log-Euclidean divergence in general have some relations to state exclusion. So, the average pairwise quantities will not provide a decent bound on those. So, I think both of those are interested in general because so the applications that one would be interested would be different. And then we also have the fact, like if I show the following, we know where the multivariate log Euclidean fidelity lies in the chain of those average ones, so it will be lower. So this can be helpful in Does that answer your question, or do you have?
Yeah, thank you. So I want to ask more about the SDP pairwise uh, fidelity. So
Yeah.
you say it is also show as a pairwise, but
Yeah.
I cannot see it. Can you explain
Yeah,
more?
actually, it's not clear on surface which whether it's a it's a pairwise quantity. So one thing that came across is like if we when we are trying to prove this quantity, which is over here, we came across that the following is also is an equivalent representation. So if I want to dig you more into the proof, is basically looking at a canonical purification of a state and then doing some manipulations over there. But it's indeed true that it's not clear, uh, that it's from the expression that it was not clear, but apparently by working out and then finding some equivalent representations, we found out it has this average pairwise quantity. So that involves some work, but the main tool was these equivalent representation, and then while we are deriving it, we were using some kind of in the this setup we can choose any purification, but when we choose a canonical purification, uh, it was easier to get the following expression. But you're welcome to look at the proof of this inequality, proof of this uh, equality, so that we have exactly how we got the other one.
I see. So it seems that you need to go through the purification so that
Yeah.
you can show that. But it's easy to imagine that if you have two pair, it's just one pair, and to do the purification. But for multiple pair, so the purification will be very large. How to align their dimension?
Actually, so like when we consider this, when I say about purification, it's for one pair. Like this phi rho I is just the purification of the state rho i's. So it's not the purification of the entire collection of states, it's just the purification of. So as we used in this proof, so we can choose phi rho I, the canonical purification that we used everywhere in quantum information. So we can use that, and then that's something that we can do. So it's not the purification of the entire collection, but it's when we make a combination of them through the Fallopian representation. So this is actually a way to compact things. It's not like we are looking at the entire purification.
I see. Thank you. So my final question is that all the fidelity do they have the like measurement equivalent form so that I can do some measurement and I can estimate them. Is there any measurement?
That's a very good question. Actually, I didn't talk about the maximum, like minimal extensions and maximal extensions. So this is related to the maximal extension where we supremize over all the measurements and looked at the classical fidelity. So it's not clear for these quantities whether it's achieved by a measurement. So this is one open question, also one open question, but there are some count examples that if we have FSDP and then look at its whether it can be achieved by measurement. So there are some count examples to some of them, but it's not clear to in general whether it is achieved by a measurement. But it's nice if it is achieved by a measurement, or get to know whether it's exactly not satisfied by a measurement. That's a very good question, and that's something that we actually try to work on. Yeah.
Thank you very much for the nice talk and answering. Thank you.
Thank you for the questions.
All right. I guess we should have time for some other questions from other people. Maybe I can ask something myself first. Hopefully this is just quick. So if the states are all pure states, I imagine most of the expressions are also simple. Like at least they simplify a bit.
Yeah, that's true. Like for the we looked at for pure states, we looked at the SDP fidelity, and secrecy based one actually simplifies, and it's not very clear with the log-Euclidean fidelities, because now it's not positive definite. So we have to do this some kind of padding and take the limit. So for that, and for the other cases.
Okay, and the one thing I wanted to ask is like, so here you have basically fidelities if all of the states are normalized. So are there definitions for unnormalized ones?
So in this work, we actually focus more on states, and then that's how we define. But some of these properties can, like, so if we don't normalize, we can't demand them to be between 0 and 1. And it can always be larger. So we remarked on those kinds of things in our work related like this direct sum properties. All these things will hold even if we consider positive semi-definite matrices in general without the trace constraint. But like we can't expect the fidelity between 0 and 1 and all this orthogonality, faithfulness. These things will be little different when we look at the generosity, but we remarked about some of those in our work. But the main priority was for to consider states.
Sure.
Because the motivation was from like probability distributions. We have this similarity measure and we want to look at the like something that reduces to them. So the focus was on states, but yeah, one could also look at.
Okay. Oh, I actually remembered something where, so when you were talking about the orthogonality, so if things are orthogonal, you want to get 0, but it's possible to get 0, but they are not orthogonal, right?
Yeah.
So I just want to have some intuition. So what's an example of a case where you would get 0, but they're not orthogonal? Is there a simple?
Yeah, the one thing is like we can look at that for probability distributions itself, or else you can look at this PIs to be diagonal states. And then
Okay.
here, these are not orthogonal, but if because we when we multiply, we will multiply 0 half 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 zeros, like we will sum over the multiplication 0 half half plus half zeros half and then half half 0, so it will evaluate to be 0, but it's not that the state p1 and p2 are not orthogonal.
Okay.
Yeah, like
Interesting.
any generalization
I
that
just don't, I'm just trying to, like, how should I interpret that? So it's sort of saying that somehow they are
yeah.
very different from each
Yeah,
other
I think
in a certain
one
sense.
way to look at is like this is lower than other fidelities. So like things can go different when it is the lowest, like it can equal to be 0. But anything other than that, when they are within a certain like inequality, as I mentioned previously, we had this inequality between the average pairwise quantities, then we can essentially, like the one here, we can obtain faithfulness and orthogonality directly because of this chain of inequalities. But the log-Euclidean fidelity was not in this, like it was a lower bound. So things can go different there.
Yeah. Okay. So yeah, maybe just one last opportunity for others. Otherwise, I guess we have taken most of the time now. Right. Okay. So I assume that maybe there's no more questions. So yeah, again, I would like to thank you for giving us a very interesting, very informative talk. Okay. I don't know if Mincho has any final words.
Thank you for having me, and
No,
it
no.
was nice
Yeah, I
talking.
think this is an interesting result, even though I'm no longer working on information theory right now. But yeah, I mean, this kind of question is always interesting to see extension beyond binaries. Yeah, nice work.
Thank you, and thank you for having me here. It was nice talking.
Hope to see you soon.
See you
Good.
soon. Bye bye.
See you. Bye bye.
See you.
Bye bye.
Bye.
Bye bye.
Thank you, everyone.
Bye bye.
Yeah.
Thank you very much.
If you can demonstrate like